So let me repeat again the motivation for providing explanations of machine learning predictions or machine learning models. These explanations are important for increasing the acceptance of these machine learning methods in exotic domains. And with exotic domains, I mean domains where we cannot expect the users to have a formal university degree in a machine learning or related field. And also, why explanations can be very useful is because they could spur validation or debugging of models. So providing an explanation that is easily understood by a domain expert might help the domain expert to maybe adjust the model. For example, in this wine farming application, so the machine learning model might predict the yield of 2,000 liters. The farmer might ask why. So the farmer wants an explanation, and the explanation would be a reference to a similar harvest last year. And this explanation might lead the user, in this case the wine farmer, to recognize that this machine learning model seemingly ignored a certain fact about the population of birds in this current wine harvest. For example, there might be a specific type of or species of birds that reduce the yield. So the model should take this into account, and we might then adapt and modify and improve the model. So up to now, the discussion was very high level, very intuitive, and in order to develop a method for constructing or computing explanations, we need to put this whole concept of explanations onto a more solid ground using a simpler probabilistic model. And in this probabilistic model, we interpret data and the features of a data point, the explanation, the prediction, and also the user background. We model all these quantities as a random variable. And of course, we would need to specify the joint distribution of all these random quantities. But for the time being, we assume that we have somehow access to the joint distribution. And given such a simple probabilistic model, we can formalize the amount of surprise or uncertainty that is intrinsic to a machine learning model or to the predictions y hat produced by a machine learning model. In particular, there are established measures of this uncertainty, for example, the entropy, or more precisely, the conditional entropy. So here we condition on this variable u, which is some user summary of a data point. So if we don't assume any user knowledge, this u might be a constant, so might be non-random. However, we will show then later a simple application in computer vision where we might come up with a reasonable choice for this user summary, which is some characteristic of a data point. And depending on this user summary, we have different measures of surprise or different levels of surprise inherent to the machine learning prediction y hat. And using this quantity, this conditional entropy to measure the surprise leads us very natural to constructing optimal explanations as a random variable, which maximizes the conditional mutual information between the explanation and the prediction of the machine learning method under the condition or conditioned on the user summary. So the important point here is that this optimal explanation, E star, is different or might be different for different user statistics or user summaries. So depending on the user, we might get different optimal explanations, which makes sense because depending if the user has some background in computer vision or in biochemistry, the user or the wine farmer might have some intuition what the prediction could be. And depending on this intuition, we should offer different explanations to maximally support or enable the user of the machine learning method. So in order to obtain an algorithm to actually compute explanations, and an explanation is here modeled as some function, which might be deterministic or a stochastic function of the data point. So this E is a random variable which is measurable with respect to the space spanned by the data point, or the features, the random features of the data point. But let's put these technical details aside. So in principle, we need to estimate this quantity, this conditional mutual information, and we can estimate this if we have access to training data. So if we have access to, for example, previous wine harvests for which we knew in hindsight the predictions, the features of the data points, and the user summaries. And then we could also say we are interested in explanations which are linear maps of the feature vector. For example, we could require the explanation to involve only up to S. S is some sparsity parameter which has to be specified. So we allow an explanation to be a linear combination of up to S features. And it turns out that maximizing the conditional mutual information, so solving this optimization problem, solving this optimal explanation problem, becomes a sparse least squares problem, or a lasso type problem for those which have had contact with sparse learning or sparse models. And we can solve this optimization problem rather efficiently using convex optimization methods. So the important point here is that this approach for constructing optimal explanations, so the explanation here is the index or the subset of features, which is the support of this weight vector, beta here. So this index of features which are most relevant as an explanation, this set of features is the explanation here in this case. And we obtain this explanation only by requiring samples, realizations of this machine learning model. So we don't need to know the inner workings of the machine learning model that delivers the predictions y hat. We only need to have access to IID samples of these machine learning predictions. So in some sense, this approach here for obtaining explanations is model agnostic. And in order to illustrate our method, we look at a particular application that is related to a recent collaboration between our group and the city planning department of Helsinki. So the city planners in Helsinki are interested in continuous monitoring of the conditions of road markings. And for this, they implement sensing campaigns using aeroplanes, and they make aerial photographs of the city area, which indicates the condition of, or allows to obtain or analyze the condition of pedestrian crossings, for example. And for this problem, or a subtask of this problem, is to learn a model for predicting the grayscale level of a certain pixel, a so-called target pixel, given the surrounding pixels. So the machine learning problem amounts to predicting the grayscale level of this pixel I, given the grayscale levels of all the neighboring pixels. And here we might consider two users, a user A, which has no computer vision knowledge. So the user statistic or user summary is a constant. And for this user, we get the optimal explanations given by the features or are given by the grayscale levels of these immediate vertical neighbors, which are colored or marked with these red boxes here. Whereas for a user B, a different user, which considers the local average of the neighboring pixels, so all the pixels in these blue dotted rectangles, the grayscale level of these pixels are averaged, and this is then the user statistic U for the user B. So this models some intrinsic knowledge or some expectation how the features, how the neighboring pixels relate to the grayscale level of the target pixel. And for this user B, we get a different explanation, and the explanation here is given in the form of the next vertical neighbors, here marked by green boxes. So this might point at, for example, that here the dominant direction of pedestrian crossings might be horizontal, because the most relevant information, even if we assume already that the neighboring pixels are a good indicator for a grayscale level, so the most relevant information is in the vertical neighborhood and not in the horizontal neighborhood. And this might point at, for example, that road markings tend to be more aligned from west to east instead of north to south. So, but this is only a small toy example to showcase our algorithm. To wrap up, we have formalized the computation or construction of explanations using a very simple probabilistic model. And in this simple probabilistic model, the act or the effect of an explanation is to reduce the conditional entropy, which quantifies the surprise in observing a prediction of a machine learning model. And this turns out to become an optimization problem. So we need to optimize a conditional mutual information. And as soon as we can somehow estimate this conditional mutual information, for example, if we have samples available, IID samples of predictions of the user summaries and the features of data points, we can actually compute approximate solutions of this optimal explanations problem. So this was only the starting point for future research. We have only scratched the surface so far. So one immediate extension would be to consider nonlinear models, so models more general than linear regression models. Then we would like to combine our approach, which is driven by information theory, with counterfactors, which have gained a lot of interest recently in the explainable machine learning and explainable AI community. Then, of course, an important question is also how to navigate or how to choose the space of allowed explanations. We always need to restrict the space of possible explanations. They need to be somewhat tailored also to the user. And so far, we don't really have a principled, nice formal approach for how to construct this space of eligible explanations. Then, of course, as I already indicated, one use of or one advantage of explanation is that it spurs feedback, or it might lead to insight provided by the human user. For example, the wine farmer realized, based on the explanation, that the machine learning model didn't take into account an important factor or important feature of a wine harvest, like the presence of birds. So how can we make this more principled, to take this feedback of the user then into account, to improve the machine learning method and also to improve the explanations of the machine learning method? So if you want to read more about the details of this approach, we have recently published a paper in the IEEE Signal Processing Letters, and you can also find the preprint of this work on arXiv. Thanks a lot for your attention.